Just like for any other equilibrium reaction, when we're dealing with acids and bases, which can go back and forth, we can write down their equilibrium constants. So one way of expressing the dissociation of an acid is we can write it as reacting with water. The H plus reacts with the H2O to produce hydronium, and then we also have the remaining ion produced in the solution. So this is our acid reaction. If we give the equilibrium constant for this, we'll have our products over our reactants. And remember, water is a pure substance here, so we don't bother with its concentration. It's actually built into our equilibrium constant. So this is our equilibrium expression. Now we're going to do just one thing different when we're talking about acids. Instead of calling this Kc, I'm going to call this Ka. And it's just going to be helpful as we do these acid-base equilibria to know whether our constant refers to the acid or the base, because we're frequently going to be talking about one acid and its conjugate base, and we don't want to get those equilibrium constants confused. Now, the shorthand way of writing this reaction is, instead of including explicitly the reaction of water, we pretend we just generate H plus and A minus. Realistically, this H plus almost immediately reacts with the water molecule to produce H3O plus. So the first setup is more physically accurate, but this is often very convenient instead of having to keep track of those extra water molecules. So in that case, our equilibrium expression would be H plus concentration times A minus concentration over HA, and they mean exactly the same thing. Now, just like with our pH and pOH, we can define a pKa for this equilibrium constant. Just take the negative log base 10 of whatever the constant is. And we can do the same thing for our base reaction. So our base reaction is where our base reacts with water and takes a proton. So we'll gain a hydrogen and we'll gain the charge that goes with it. And then the water will be reduced to OH minus. Now, just like for the acid, we can write down an equation for this, and the water will drop out of the equation. Just like for the acid, we'll go ahead and give this a special name, and we'll call it Kb. It's still just a perfectly ordinary equilibrium constant, nothing special about it at all. We just changed the subscript to remind ourselves that it corresponded to a base. And we can define the pKb for this base is equal to negative log base 10 of whatever our constant Kb turns out to be. One thing that's slightly different about doing equilibria problems with acids and bases is that oftentimes we'll be given the concentration of the H plus as a pH, or the concentration of the OH minus as a POH. Other than that, they're fairly equivalent. So first thing you might want to do in one of these problems, if you're given a pH or a POH, is go ahead and convert that to a normal concentration so you can use it as you normally would. The definition of pH is that it's equal to negative log base 10 of the H plus concentration. To make this logarithm go away, we need to take 10 to the power of that logarithm. And since this is an equation, we need to do it to both sides. So let's move the minus sign over to the left side, and then take 10 to the power of the left side and 10 to the power of the right side. So then we will have H plus concentration pulled out of that logarithm, and it will be equal to 10 to the minus the pH. 10 to the minus 4.95 is 1.12 times 10 to the minus 5, and we'll stick on units of molarity because this is a concentration. Now we can solve this as a typical equilibrium problem. So we'll go ahead and pull out our ICE table, and initially we have 0.2 molar concentration of our hydrocyanic acid. And at the very start, none of it's decomposed to make any H plus or Cn minus. Then for every mole of hydrocyanic acid which decomposes, we'll get back mole of H plus, or of Cn minus. And our final value will be 0.2 minus x for HCN. For H plus, it will be equal to x, but we also know that the final concentration of H plus is 1.12 times 10 to the minus 5 molar, which means we know what x is. This has to be equal to x. So we can go ahead and plug that in to our equilibrium expression. So our constant is going to be products of a reactant, so it's going to be these numbers divided by this number. So this, if we write it algebraically, this is our x. So we have x times x over 0.2 minus x. And we can plug in this 1.12 times 10 to the minus 5 for x. And in that case, we get our equilibrium constant that we are after of 6.3 times 10 to the minus 10. That's pretty handy for any acid or base. You pull out your pH meter and you know what the initial concentration is. You can figure out what the equilibrium constant is for that substance. Another way we might characterize a substance which includes an acid or a base is we might characterize it by how much of the acid or the base decomposes. And this is called its percent ionization. It's just the percentage of the original substance which converts into ions. And we'll take the amount which is ionized and divide it by the original amount and then multiply by 100 to turn that fraction into a percentage. So for example, try and figure out what the percent ionization of hydrocyanic acid is from our previous problem. Now we know what the ICE table is for this. Now this ICE table, this minus x is how much of our HCN is lost, how much of it converts over to the right side into H plus and Cn minus. So that's the amount which dissociates. So we can go ahead and plug in our x value, which we now know, divided by our original quantity, which is this 0.2, times 100. And that gives us a percentage of 0.0056%. So a tremendously small quantity of this HCN actually goes forward and becomes H plus and Cn minus. The vast majority of hydrocyanic acid is just going to remain as the HCN molecule and not add any acidity to the solution. So this is what's called a weak acid, because it weakly dissociates. It only partially ionizes in the solution. So we've decided that acids and bases are important enough examples of the equilibrium reactions to warrant their own independent discussions. This is also true of water. Now, water undergoes what's called autoionization. A water molecule can react with another water molecule, and one of them acts as an acid and donates a proton, and the other one accepts it, and so then we get H3O plus and OH minus. And it's common to abbreviate this reaction and just say we have one water molecule which breaks apart into H plus and OH minus. And these both mean the same thing. This is more physically accurate. This you have to keep in the back of your head, that this H plus actually reacts with a water molecule soon after forming. Now if we write down the equilibrium constant for this, again, this is just a normal concentration equilibrium constant. There's nothing special about it other than that we're going to change the subscript just to remind ourselves that we're talking about water. And if we work it out, we have H plus concentration, OH minus concentration, divided by the H2O concentration, which is a pure liquid, so we're just going to set that equal to 1. So we have K waters equal to H plus times OH minus concentration. Now if we measure the concentration of each of these, and we get our equilibrium constant, turns out that it's 10 to the minus 14 at room temperature, which we're going to define as 25 degrees Celsius. And this is a very handy relationship. We're going to frequently assume that we are working at this temperature in a laboratory so that we can use it. And this is actually where our equation pH plus POH equals 14 comes from. If we just take log base 10 of both sides, we'll get this equation here, which is a very handy relation. So for example, let's figure out what the pH is of pure water. Now we'll start this off as an equilibrium problem, since we know that water exists in equilibrium with these ions. And we want to figure out either the H plus concentration or the OH minus concentration so that we can get the pH. So initially, we'll start off with none of these, and then some water will decompose, and it will produce some more H plus and some more OH minus. Now if we plug that into our equilibrium expression, we'll get x squared is equal to K water, which is 10 to the minus 14. And so the square root of that is 10 to the minus 7. And that's going to be how much H plus concentration we have. That's also how much OH minus concentration we have. Now we can stick that into our pH expression. So negative log base 10 of 10 to the minus 7 is 7. So this is the pH of neutral water at 25 degrees Celsius. If we're at a different temperature, then water will have a different neutral pH, but probably still reasonably close to 7. Another example, figure out what the pH is of a 0.07 molar solution of calcium hydroxide using our relationship we found between H plus OH minus and K water. So we recognize calcium hydroxide as one of our strong bases, which means we can get the OH minus concentration just doing straightforward stoichiometry. When a calcium hydroxide dissociates, we'll get calcium 2 plus and 2 OH minus ions for every 1 calcium hydroxide we started with. Now we know we have 0.07 moles per liter of calcium hydroxide. So to convert this moles into moles of OH minus, we have a 2-to-1 ratio. And so we wind up with 0.14 moles per liter of OH minus. Now we can convert this into H plus concentration using our equilibrium constant for water. So if we solve for the H plus concentration, that will be 10 to the minus 14 divided by the OH minus concentration, which we just figured out was 0.14. And so that gives us a concentration of H plus of 7.14 times 10 to the minus 14. And to get that as a pH, now we just take negative log base 10 of that 7.14 times 10 to the minus 14. Now we get a pH of 13.15. Now just a logical check on our work here. Calcium hydroxide is a base, so we expect to get a basic pH, one that's greater than 7. And in this case, we certainly do. We have a very basic system of 13.15. So that's a reasonable check that we haven't messed something up. There's actually an intimate relationship between these 3 equilibrium constants that we've introduced and given special names to. Now to see this, let's start just by considering one of our Bronsted-Lowry acid-base pairs. So let's look at ammonium. So this is an acid and its conjugate base is ammonia, NH3. Now if we write down the reactions for these, for the ammonium, it reacts with water to produce H3O plus and ammonia, its conjugate. Now the ammonia, it would react with water to produce NH4 plus, its conjugate, and OH minus in solution. What about the total reaction? If we treat these as 2 steps and add them together, we know the equilibrium constant for NH4 plus is Ka, and for NH3 is Kb. And we know when we add reactions together that the final equilibrium constant is the multiplication of all the reactions that we added together. Now if we add these reactions together, looks like we have NH4 plus on the right and the left. So that should cancel out. We have NH3 on the right and the left. So that should go away. Now we have two H2O molecules on the left, and then we have our hydronium and our OH minus on the right. We should recognize this. This is our dissociation of water by autoionization. And so this is going to have an equilibrium constant of K water. So we have just proven that K water is equal to Ka times Kb. This is a very handy equation because K water is a constant, so as long as we know either Ka or Kb, we can always find the other one, the value for the conjugate substance. And just like we did with the expression for K water related to OH minus and H plus, if we take the log base 10 of both sides, then we get a very handy relationship. The pKa plus the pKb also comes out to a total of 14. So this, if we're dealing with pKs, then we can use this expression. If we're dealing with the original equilibrium constants, we can use this expression. An example of how this is useful, let's say that we want to find the Kb of our fluoride ion. Now what we'd probably start doing is trying to look this up in our table, and in most cases I think we would find that it's not there. It's not listed in the table. Well, the reason it's not listed is because it's more common to be dealing with its conjugate in the acid form. So what we want to do instead is look up the Ka of the conjugate acid, which is going to be HF. That's fluoride plus the proton. And when we look this up, we do find it. We find it has a Ka of 6.8 times 10 to the minus 14. So we can convert this into Kb using our K water relationship. So Kb will be equal to K water divided by Ka, be equal to 10 to the minus 14 over 6.8 times 10 to the minus 4, which is the Ka we looked up for the conjugate. And so we get a Kb of 1.5 times 10 to the minus 11 for fluoride.